Lesson 1. Bits and Bytes. All memory inside of a computer is made up of switches. Just like a light switch, these switches can be either on or off. Numerically, we represent these states by 1 or 0 respectively. Since these switches have two states, they are said to be binary. A single memory location in a typical computer is comprised of 8 of these switches, which represent what is called a byte of data. With 8 switches, we have 2 to the 8 equal to 256 possible states. Each of these states corresponds to an integer between 0 and 255 inclusive. Numbers that we normally use are written in what is known as decimal notation. Each successive digit in the decimal format corresponds to the next higher power of 10. The lowest digit is called the ones digit, the next is called the tens digit, the next the hundreds digit, and so on. Each of these corresponds to a multiple of a power of 10. So 385, for example, can be thought of as 3 times 10 to the 2, plus 8 times 10 to the 1, plus 5 times 10 to the 0. Similarly, the switches in a byte represent a binary number where the digits can only be 0 or 1 instead of the 0 through 9 that we have in decimal. Each digit in a binary representation is called a bit, which is short for binary digit. Since there are only 2 possible states, digits in binary represent powers of 2. This byte, for example, represents this binary number, which is 2 to the 4 plus 2 to the 3 plus 2 to the 0, which equals 16 plus 8 plus 1, or 25. Likewise, this byte, which consists of all ones, represents this binary number made up of 8 ones. This is the largest number that we can represent in a byte, and it is equal to the sum of the powers of 2 from 7 to 0. The total comes to 255. To count in binary, we begin with 1, add 1 to it, and we get 2 in the ones place. This works just like addition in decimal when we get 10. In fact, 1 0 is 2 in binary and looks just like 10 in decimal. With 2 in the ones place, we carry to the 2's place to get 1 0. Adding 1 to this, we get 1 1. Adding 1 again, we carry to the 2's place. Now we have 2 or 1 0 in the 2's place. So this carries to the 4's place to give us 1 0 0 or 4. That should give some idea how to work in binary. In general, we can add 2 binary numbers like this, 1 0 1 1 and 1 0 1 1 0. These numbers represent 8 plus 2 plus 1 equal to 11, and 16 plus 4 plus 2 equal to 22 respectively. Notice that 22 is 2 times 11, and its binary representation is exactly the same, but shifted left by 1 digit. Multiplying by 2 in binary is similar to multiplying by 10 in decimal. Now if we add these two numbers, we get 1 0 0 0 0 1, which equals 33. Since it is long and cumbersome to write 8 digits for a byte, computer scientists prefer a more economical representation. Breaking a byte into 2, we have 2 4-bit sets, which are referred to as nibbles. A nibble, or 4 bits, can take 16 distinct configurations. Each of these 16 configurations can be represented by a single-digit character like this. Since there are 16 possibilities for each digit, this representation is called hexadecimal. A hexadecimal digit uses decimal digits to represent 0 through 9, and A through F to represent 10 through 15. With hexadecimal, we can represent each byte as 2 digits instead of 8. For example, this byte, 01001101, can be written in hexadecimal as 4B. Hexadecimal numbers are base 16, just like binary and decimal numbers are base 2 and 10 respectively. That is, each digit in hexadecimal represents a multiple of a power of 16. For programming purposes, we prepend 0x to hexadecimal numbers to signify the number base 16, so that 4b is written as 0x 4b in C++. This allows us to distinguish the number base so that we know that 1 1 equals 10 plus 1, and 0x 1 1 equals 16 plus 1, which is 17. This concludes the lesson.